Welcome back, hope you're doing well. Previously we looked at and evaluated the loss function of various linear models with respect to different weights. We saw that given previously labeled data, there exists weight parameters for a line that will yield the smallest error. The question remains, how do we train a model to determine the weight parameters which will minimize our error function the most? Well, this is where we introduce gradient descent. The way this works is that first your linear model will begin with random initial parameters. Recall when we initialized a model with the linear function, it indeed gave us random initial parameters. Let's ignore the bias value for now. And based on the error associated with this initial parameter, w, we want to move in the direction that gives us the smallest error. The trick is, if I take the gradient of our error function, the derivative, the slope of the tangent at the current value that I'm at, this derivative will take us in the direction of the highest error. So what we do is we move in the negative of the gradient. This will take us in the direction of the lowest error. So we take the current weight and we subtract the derivative of that function at that same point. This will take us in the direction of the least error. We are descending with the gradient. However, to ensure optimal results, one should descend in really small steps. As such, we will multiply the gradient by a very small number, known as the learning rate. The value of the learning rate is empirical, although a good standard starting value tends to be 1 over 10, or 1 over 100. The learning rate needs to be sufficiently small since as the line is adjusting itself, you never want it to move too drastically in one direction, as that can cause for unwanted divergent behavior. Throughout the course, you will learn to adjust the learning rate based on empirical results, and we will code a gradient descent algorithm in the next few videos, but to just end this lesson, and to follow through with our gradient descent example, let us refer to a demonstration on Excel in order to simply visualize the effect of gradient descent. Alright, as you can see on top, we have the coordinates of the point themselves, x and y, and below I've set up two columns, the weight and the error. The initial weight is clearly negative 1.5, and I've set up the spreadsheet such that the second weight is equal to the value of the first weight minus the derivative of its error function at that weight times a learning rate of 0.01 to give us the new weight. Thus, at each step, we are moving in the negative of the gradient. And if we do it for one step, notice that the error gets smaller. And if we keep doing it for subsequent cells, notice how the weight eventually converges to -1, such that the error at that value approaches 0. This is consistent with the graph that we observed earlier, as a weight of -1 would indeed yield the smallest error for the point -3 and 3, as we saw in the last video. Alright, so clearly gradient descent, descending in the negative of the gradient, is a very effective approach in training our model. Don't worry too much about this Excel sheet. This was purely for visualization purposes. If you want, I can include it as a resource for this lecture if you wish to play around with it. In the next few videos, we will work our way up to implementing gradient descent into our code. But before doing so, let us discuss the mean squared error. We'll do that in the next section.